Welcome you all. I am Professor Sri Krishna Gosavi from Walchand Institute of Technology, Civil Engineering Department. Today we are going to see the analysis of prestressed concrete members by stress concept. So here by using the stress concept method we are going to solve the problem. Okay. So now at the end of this session, the student will be able to analyze prestressed concrete sections by the stress concept. So by using the stress concept, the students can solve the problems of prestressed concrete members. They will be analyzing the prestressed concrete members. That is the learning outcome of this whole session. And now the next is the numerical, which we are going to which we will solve here right now. And the numerical is the prestressed concrete beam 400 mm by 600 mm in section has a span of 6 meters. It carries a load of 16 kilonewton per meter including the self weight of the beam. The prestressing tendons are located at 200 mm from the soffit of the beam, which provides the effective prestressing force of 960 kilonewton. So we determine the extreme stresses in the concrete at the midspan section. In that numerical, it is given that a beam is there, which is prestressed concrete beam is there, which is having a section of 400 mm by 600 mm. These are the cross-sectional dimensions, and the span of the beam is 6 meters. So here I have drawn the diagram of the beam. Here you can see the span of the beam is 6 meter. Then here the prestressing force is applied, which is of having the magnitude 960 kilonewton. Then this red line, this is nothing but the tendon which is placed below the neutral axis of the beam. This dotted line is the neutral axis of the beam. And here you can see at the top a load of 16 kilonewton per meter is applied. And now as mentioned in the problem, the total depth of the beam, so top to the bottom, the total depth is 600. So from the neutral axis we have taken the half of the distance, that is 300 from the neutral axis. The topmost fiber is at a distance of 300, and from the neutral axis the bottom fiber is at a distance of 300. Okay, so now by using the stress concept we need to calculate the extreme fiber stresses. So we know that in the stress concept, the stresses, the resultant stress, if we want to calculate the resultant stress, the resultant stresses at top and bottom, the general formula is P by A. P by A means direct stress. Then P by Z. P by Z means bending. P by Z means the stress due to eccentricity. The bending moment which is generated due to this eccentricity, here also you can see E is equal to 100 mm. Due to this bending moment is getting generated in the section, and then due to that bending moment the stress is getting developed over here. So this is the PE by Z is the stress due to the eccentricity, and then M by Z. So M by Z is the bending stress which is due to the dead load and live load. So there is, as we can see here, the tendons are placed below the neutral axis. So the P by A is the direct stress which is always positive, whether you are taking it above the neutral axis or below the neutral axis. This is compressive, so this is positive. Remember that whenever the stresses are compressive, then it is positive, and whenever the stresses are tensile, then it is taken as negative. So P by Z, here you can see now the P by Z is negative at the top and positive at the bottom. The tension is created at the topmost fiber, so that is why it is negative at the top, and the compression is at the bottom fiber. So here you can see the prestressing force is applied over here, and now due to the prestressing force, see this force will act in this direction, okay, towards the neutral axis in this direction. So this will try to hog the beam like this. So if this type of profile is there, then you can see tension is at top and compression is at bottom. So if the tension is at top, then negative sign must be at the top, and compression is at bottom, so positive sign must be at the bottom. So therefore this P by Z is minus and plus, minus at the top, plus at the bottom. Then M by Z is the due to this load. Here you can see 16 kilonewton meter load is acting over the beam. So due to this load, the bending profile of the beam will be like this. it is like a sagging profile. So compression is at the top, tension is at the bottom. So compression is at the top, so plus will be at the top, minus is at the bottom, so it is plus and minus. So in this way the resultant stresses are calculated in this stress concept. Now coming back to the problem, so here from the given information we can calculate area. So area is equal to 400 by 600 are the cross sectional dimensions. So it will be, if you do this calculation, it is 2.4 into 10 raised to 5 mm square. This is the area. Okay, so after the area we can calculate the section modulus. So section modulus, it can be calculated as section modulus Z. So the formula for section modulus, if the rectangular section is there, it is BD square by 6. Now just you need to put the values. BD square by 6 means B is 400, D is 600 square divided by 6. So therefore Z is equal to, so we will get the value of Z as 2.4 into 10 raised to 7 mm cube. So this is the value of section modulus. Now here you can see we calculated the area and then section modulus. Okay, after this calculate the bending moment. So bending moment M is equal to calculate the bending moment, formula is WL square by 8, and here in the numerical itself it is given that this load whatever 16 kilonewton is acting, it is inclusive of self weight of the beam. So self weight of the beam itself, it is considered in this 16 kilonewton per meter load. So that is why we are going to take it directly. So it is 16 into 6 square divided by 8. So therefore M is equal to, bending moment is equal to, so finally we get the value of bending moment after solving this, it is 72 kilonewton meter. This is the value of bending moment. Okay, now after this we are going to calculate the direct stress. Okay, we are going to calculate the direct stress. So here direct stress is equal to calculate direct stress, we know the formula, it is P divided by A, which is equal to, the pre-stressing force is given in the numerical and it is 960 kilonewton. So P is 960 kilonewton to Newton in multiplied by 10 raised to 3 divided by area. Already we have calculated the area, 400 by 600, it is 2.4 into 10 raised to 5. So when we solve this, we will get the value of this as 4 Newton per mm square, that is 4 megapascal. And I have already told you direct stress is the compressive stress, it is always the compressive stress. So that is why this value is plus, this is plus, because it is compressive. If the stress is tensile, then we will take it as a minus. So now here after this direct stress, we will calculate stress due to eccentricity. So here now stress due to eccentricity. The stress due to eccentricity, it can be calculated by using the formula PE by Z. So I have told you already, it is minus at the top and plus at the bottom. So which is equal to, the value of P is 960 into 10 raised to 3 into eccentricity E is 100 mm, which is given, divided by Z. We have already calculated the value of Z, 2.4 into 10 raised to 7. So if you solve this, we will get the value, it is 4 megapascal. So minus plus means it is minus at the top. So tensile at the top fiber and compressive at the bottom fiber. Top fiber means fibers which are above the neutral axis, and bottom fibers are fibers below the neutral axis. So above the neutral axis it is minus 4, below the neutral axis it is plus 4. This is the stress due to eccentricity. After that, calculate the stress due to bending moment. stress due to bending moment, which can be calculated as stress due to bending moment. It is m by z. This stress can be calculated as m by z plus and minus. So it is at topmost fiber, at top fiber it is plus, at bottom fiber it is minus. So if you put the value, we have already calculated the value of m is 72 kilonewton meter, so 72 into 10 raised to 6 to convert it into Newton mm. Z is equal to 2.4 into 10 raised to 7 mm cube. So after solving this, we will get this value as 3 megapascal. This value is 3 megapascal plus minus 3. So now we got the value of all the stresses. We know the value of direct stress, that is P by A. We know the value of stress due to eccentricity, that is P by Z, and we know the value of stress due to bending moment, that is M by Z. Now it is time to calculate the final resultant stresses at topmost fiber and at bottom fiber. So resultant stresses at top fiber and bottom fiber. So here I will write resultant stresses. Resultant stresses. So at top, resultant stress at top, sigma T, we will call it as sigma T. So the formula for this is P by A minus P by Z plus M by Z. Just we need to put the values. So which is equal to P by A is 4 minus P by Z is 4 plus M by Z is 3. So the answer we are getting over here is 3 megapascal, that is Newton per mm square. This is the resultant stress. Now next, at bottom or soffit, sigma B. So the formula for this is P by A plus PE by Z minus M by Z. So if we put the values over here, P by A is again 4, PE by Z is again 4, M by Z is 3. So if you put these values, you will get the final answer as 5 Newton per mm square. So now we got the values of resultant stresses, that is at the top it is 3 MPa, that is 3 Newton per mm square, and at bottom it is 5 MPa, that is 5 Newton per mm square. Now after calculating all these stresses, now these are nothing but the resultant stresses at extreme fiber. Okay, so the resultant stress at the extreme fiber of the beam at the top, it is 3 Newton per mm square or 3 megapascal, and the resultant stress at the soffit of the beam, at the given loading condition is 5 Newton per mm square. Okay, and at the last, after this, you need to draw the resultant stress distribution diagram. So this diagram is already drawn here. You can see in this way we need to draw the diagram. So these are some of the references for this stress concept. You can use the RCC structural element, Bhavikatti, Ramamrutam, Punmiya, Jain. So many textbooks are there and reference books are there. This can be used for the references. Thank you.